Yes, so welcome everybody to this webinar. It's one of the two final webinars from the Horizon 2020 CEMCAP project that we're organizing today. My name is Kristin Jordahl. I've been the coordinator of this project. I will give you first an overview of CEMCAP, technological achievements and key conclusions. Right after my presentation, we will have a presentation on the Oxy Fuel Technology, and thereafter, as Ann said, we will have time for questions. This is to be a little bit more efficient. Then after this question session, Mari Wollsen will present the research done on CO2 capture retrofitability to cement plants. And there will be another round for time for questions after that. And, thereafter, we end the first webinar. Then we have a second one at 1 o'clock this afternoon. Okay, so I will get started and talk about CEMCAP, the technological achievements and key conclusions from this Horizon 2020 project. So about the CEMCAP project, it has had a duration of 3.5 years. We started in May 2015. We're ending October, so on Wednesday this week, 31st of October, we're ending. We have had a budget of 10 million euro. The EU contribution has been around 8.8 million euro. We have also had a Swiss contribution for our Swiss partner ETH in Zurich, and there's been some industrial in-kind also. You can see the consortium to the right with the partners and the countries that have been part of the project. And the main objective of CEMCAP has been to prepare the ground for large-scale implementation of CO2 capture in the European cement industry. So it's all been about cement. And something that's been very specific about CEMCAP has been the consistency of the project, that we have done analytical research, talked about performance, retrofitability analysis. We have also had experimental research, quite a lot of experimental research. And to have a consistency in this so that the experimental research actually can feed into the analytical research and that we can draw a consistent conclusions and come with recommendations afterwards and have this tight connection. We have established a common framework document, which you can see the cover page on to the right. It's called the CEMCAP Framework for Comparative Techno-Economic Analysis of CO2 Capture from Cement Plants. This is a publicly available document that specifies a reference cement kiln. How do we calculate the CO2 capture from the different, for the different capture technologies? How do we compare them? How do we calculate things like pumps or heat exchangers? Everything is in there to make it transparent and make sure that everybody in the project work on the same basis. But it's also useful if you want to study CO2 capture from cement outside the CEMCAP project. It's available in the Zenodo repository that you will have a link to on the last page of my presentation. So in CEMCAP, we have investigated, we started with saying that we would investigate 4 CO2 capture technologies in CEMCAP, which is the Oxy Fuel, then the post-combustion capture technologies, chilled ammonia process, membrane-assisted liquefaction, and calcium looping. But in calcium looping, it became clear that we actually have 2 different concepts. We talk about tail end, that we put at the exhaust pipe of the cement kiln, or the more integrated calcium looping technology. And what's very important is that we have fundamentally different capture technologies in CEMCAP that have different angles to approach this problem. How do we separate CO2 from the cement production? They have different strengths and they have different challenges. And as an example, we can look at the energy provision. That Oxyfuel consumes power for the air separation unit and from the CO2 processing. Chilled ammonia process, it's like a solvent technology. It mainly consumes steam, but also some power for cooling. It's a chilled ammonia process. The membrane-assisted liquefaction is a hybrid technology that consumes power for pumps and refrigeration and compression. And then the calcium looping requires both fuel for the calcination reaction and also power for the, mainly for the air separation unit process. And what remains a fact is that CO2 capture requires energy and costs money. CEMCAP cannot change this. We did not change this fact, of course. That would be thermodynamically impossible not to use energy to capture CO2. But we have decreased the uncertainty about the numbers for cement industry. We have made consistent and transparent analysis and comparison. So I will present the different capture technologies in CEMCAP now briefly. Start with the chilled ammonia process, CAP. It uses ammonia for CO2 capture. Ammonia is a commodity chemical which is globally available, very much used for different purposes, and it's chemically stable. So the principle is that aqueous ammonia or ammonia water mixture absorbs CO2 in an absorption column that you can see on this picture. And then we regenerate the solution or release the CO2 through heating at pressure, and in regeneration, then we add steam to heat up the solution and then further compress the CO2. It releases a very pure CO2 stream, this process. The experimental work has been done at the GE Technical Center in Växjö, Sweden. It still says Alstom on the sign. You can see that this was formerly Alstom Power. And the research that's been done is to, in pilot scale in this lab, large pilot scale, investigate process differences between cement and power, because chilled ammonia had been tested for power before, CO2 concentrations up to perhaps 14–15%, which is relevant for coal. And also the thermodynamic and kinetic models have been developed to describe how the reactions occur. And there's been a process optimization for the cement application, which was new to chilled ammonia. So the achievements that have been done in CEMCAP is that the process models have been validated against experimental data, and that we have exploited, or chilled ammonia has exploited high CO2 concentrations capture, highly efficient capture. You can see that for the power plant was around 14% CO2, and for cement plant, 18 and 22% CO2 concentration have been investigated, and the exergy consumption then has gone down. And the functionality of the chilled ammonia has been validated. The process units that are affected by new flue gas composition has been tested. That's the direct contact cooler, the absorber, and the water wash sections. There are other sections, parts of the chilled ammonia process that remain the same. And chilled ammonia is ready for on-site demonstration after what's been done in CEMCAP. You can see here a picture from the Mountaineer Power Plant in West Virginia in the United States. It's a coal-fired power plant where chilled ammonia was tested in 2009 to 2011 already for 8,000 hours. Then for the next capture technology, perhaps the least known, it's hybrid technology that we call membrane-assisted CO2 liquefaction, in brief MAL. And the principle is that the flue gas is CO2 enriched through membranes to low-end oxyfuel conditions, as we call it, then compressed, cooled, and condensed. You can see in the diagram on the right-hand side, CO2 concentrations typical for coal, around 15%, as we said before. For cement kilns, cement plants, CO2 concentration is higher. And then the thought is that if we can use a membrane that's CO2 selective, not perfectly CO2 selective, but polymeric membrane, we can enrich the CO2 concentration and get to the lower range of oxyfuel. For cement, oxyfuel would rather be at 80%, but what Johannes will talk about later. But for with membranes, we aim to come up somewhere between 60–70%. And then we're at oxyfuel conditions. As the green arrow shows, we can then compress the permeate, liquefy and purify the CO2 by venting off the gaseous impurities and end up with a liquid CO2 at high pressure and purity. So the research that's been done is that membranes have been tested in lab. We developed the process schemes for how to put these two components together, the membrane and liquefaction, and demonstrated CO2 liquefaction on pilot scale. And the achievements in CEMCAP has been the testing of polymeric membranes. Two membrane materials, one commercial and one pre-commercial, have been tested, and it was found that the CO2 over nitrogen selectivity was sufficient to have a sufficient CO2 concentration for the efficient liquefaction. And the operability of the CO2 liquefaction has been demonstrated in a 5 to 10 ton per day scale. This is the rig you can see to the right is a recirculating rig, so it's actually more complex to operate than what a rig would be on site, since we recirculate the CO2 and the nitrogen all the time. So the binary CO2 and nitrogen mixtures with CO concentrations that are relevant for the applications have been tested, and we have measured a very high CO2 product purity, up to 99.8 CO2. Next technology, calcium looping capture. There will also be a presentation about calcium looping in the second webinar. The principle is that CO2 is captured in a carbonator through the reaction of calcium oxide to calcium carbonate, and then CO2 is released in a calciner through the opposite reaction. So calcium carbonate is actually the raw material that you also use in the clinker burning process in the cement kiln, which means that these seem to fit very well together already on an intuitive level. And the research has been the two different configurations were investigated, the tail end and the integrated and train flow calcium looping. Experimental investigations were done on two scales, more fundamental at 30 kilowatt rig, and then on a pilot scale in a 200 kilowatt rig at University of Stuttgart. And I said two configurations were investigated, and the tail end, the circulating fluidized bed, is the most mature. It derives from previous research on CO2 capture from coal-fired power plants with calcium looping. And then the more energy efficient integrated and train flow was also investigated in lab. And high CO2 capture rates up to 98% were demonstrated with tail end calcium looping. And that was in accordance with what could be seen already from theory with the ideal or the models that were developed by the partners. So this was confirmed with the high CO2 capture rate, and we can say that after the CEMCAP research, this is a technology that's ready for on-site demo. And then there's also been the integrated and train flow calcium looping, which was not taken beyond lab scale in CEMCAP, but there has been a spin-off afterwards. This has been found very promising. And the Horizon 2020 Clinker project started about a year ago, where the goal is to have an on-site demo of this technology. You can see to the low right-hand side model that was developed to investigate the reactor length of the CO2 capture efficiency as a function of the reactor length, which seems to level out at around 90% CO2 capture. I will also have one slide about Oxyfuel, even if you have a full presentation afterwards, but I included that for completeness. In CEMCAP, the Oxyfuel burner was tested under cement conditions in an existing rig that was rebuilt, and there were also CFD simulations to scale up the results to full scale. There was testing on the Oxyfuel calcination to look at the temperature difference between calcination under air conditions and under Oxyfuel conditions. And there was the on-site testing of the Oxyfuel Clink prototype at the Heidelberg cement plant in Hanover. And this has been complemented by the existing ECRA VDZ Oxyfuel process model that was updated and in accordance with the experimental results. So that was what we did in CEMCAP. Where do we go from here? Well, we can see that the next step for the different technologies for Oxyfuel, ECRA, one of the CEMCAP partners, has a CCS project that has plans for two demonstrators at Colleferro in Italy and at Retzna in Austria. For chilled ammonia, CAP, a pilot plant of 100,000 tons of CO2 per year has been envisioned, and GE has the full EPC capacity here. For membrane-assisted liquefaction, we can see that the next step would be to have on-site screening of different membranes at operating cement kiln to see about the durability, the CO2 separation capacities, and so on. And the liquefaction then needs to be tested and demonstrated with the flue gas impurities that you get with the on-site testing of membranes. So far, we only tested it with CO2 and nitrogen. Tail end calcium looping, as we said, it's ready for on-site testing. And for the entrained flow calcium looping, this is being brought to on-site demo in the Clinker project. But after we have captured the CO2, we need to do something. This is all about climate protection. But at the same time, it's been thought and said that cement production is a potential carbon source in a fossil-free future. 2/3 of the CO2 from cement production, roughly, comes from the calcination, calcium carbonate to calcium oxide. But then again, CO2 is a very stable molecule, and the conversion processes are normally highly energy intensive. So what was done in CEMCAP was that 16 different CO2-based products were evaluated. You can see the summary to the right that for each product, the market, the energy demand, the maturity, and the price were assessed and described. And the conclusions from this very comprehensive work is that current CO2 utilization routes, or CCU routes, they have limited opportunity for climate change mitigation in the cement industry context. There is a lot of CO2, limited market, and so on for the product. So it's likely that less than 10% of CO2 from a cement plant can be used for CCU. But there can be some niche applications with positive CCUS business cases that can help the realization of CO2 capture. But the conclusion is that CCU always needs the S for storage, because either the market or the raw material availability poses limitations on the amount of CO2 that can be utilized. And in addition, we also have the energy demand, and where do we get the energy from for the conversion processes. So to sum up, the CEMCAP project is that we have expanded the knowledge base for future CCS deployments. We know more about CO2 capture from cement and how different technologies behave relative to each other than we did when the project started. We deliver what we call a techno-economic decision base for retrofittable CO2 capture from cement. You will hear more about that later today. And the framework that I mentioned in the beginning of my talk and the results together, these are suitable for in-house evaluation of CCUS in the cement sector. And just please use them and make use of what we've done in CEMCAP if you want to investigate CO2 capture from cement further. So we have provided 5 candidate technologies for CO2 capture demos in the cement sector. And in addition, we also have the NorCem project. They are doing a feed study for full-scale CO2 capture with an amine technology. And there is also the Horizon 2020 project LEILAC. They are preparing to run a demo with indirect calcination. So it's not full CO2 capture, but they're going to capture very pure CO2 from that process. And that project is still ongoing. So altogether, I mean, this means that we have 7 technologies ready for or already progressing towards at least demo or even full scale in the NorCem case. But we can also see that technology can only bring it this far. We need funding and we need an industrial ownership, the industry, to say that, yes, now we'll do this if we're going to move on to demonstration. And if we're going to move on to full scale CCS, we also need the business models, so that we can have a case that somebody actually wants to build. Then you can also see down to the right-hand side a summary of where CEMCAP is positioned in development of CCS for cement industry. We started with the ECRA NorCem CCS project and the cement industry commitment to climate protection, and also several researchers and industry that had experience from FP6 and FP7 CCS projects for the power sector and laboratories and knowledge about these technologies. We have worked very efficiently together for research and innovation in CEMCAP and matured CO2 capture from cement, and we provide guidelines for cost and resource efficient CO2 capture. Next step would be CO2 capture demos on the road to accelerated and widened deployment of full-scale CCS. But as I said again, we need the funding, we need the business models. That was all what I had to say. This is an acknowledgement to all the CEMCAP partners who made all the research in CEMCAP possible. It's the cement producers Italcementi, NorCem and Heidelberg Cement. We have the technology providers GE, IKN, and ThyssenKrupp, and the R&D providers SINTEF, ECRA, TNO, ETH Zurich, University of Stuttgart, Politecnico di Milano, CSIC, and VDZ, and SINTEF has been the coordinator. Of course, we also want to acknowledge the funding from the European Union, Horizon 2020, and the Swiss State Secretariat for Education, Research and Innovation. And if you want to find out more about CEMCAP, we have a website. We have a community in Zenodo where we upload all the public deliverables once they are approved by the European Commission. And we still have some activity on Twitter also. But that's all what I had to say. And please note your questions if you have any, and we will move on directly to the Oxyfuel presentation. Please.
Okay, thank you, Christine. So now I'll make Johannes presenter. Now you should be able to present Johannes.
Of the cement industry, and they're in the Environment and Technology department. I will briefly introduce you to the Oxyfuel technology, what it is about. This technology for CO2 capture tries to concentrate CO2 in the process. And this is done by replacing the air through oxygen, which is normally, and the air is normally used for burning of fuel, and you do this now in pure oxygen. But the nitrogen, which is in the air normally, is then replaced by recirculated CO2. And thereby the concentration of CO2 can be increased from normally 20% to about 80%, which then allows for very energy efficient CO2 concentration and purification to very high concentrations in the end. What did we do on the Oxyfuel capture technology? We had 3 different projects or work packages in CEMCAP which demonstrated key technologies for the Oxyfuel capture process. This was first on the calcination process, and there we were interested in knowing how the temperature increase, how much it is, and how it is in a real system which replicates the industrial environment. And the second was on the kiln main burner in the cement kiln. This is the point where the heat transfer for the clinker burning is provided. And therefore, here the interest was especially how the heat transfer and the profile of heat in the kiln is adjusted when we move from normal air burning to the oxyfuel environment in the kiln. The third key technology was the cement clinker cooler. And this was really tested. You see this on the left side in the cement plant at Hanover of Heidelberg Cement. And we had hot clinker from the kiln falling into this pilot and prototype installation and could then test how the clinker cooling performs under these oxyfuel conditions. All 3 experiments were successfully operated in the industrial environment or in an environment which is replicating the industrial situation. We have thereby achieved to really advance these technologies to the technical readiness level number 6. And the next step is really the application in a full-scale system. In addition to that, the results from the testing of the key technologies was used in modeling of the entire oxyfuel process. So the individual components were compiled together in the model, and this applied 55% of recirculation of CO2. We achieved 80% CO2 enrichment in the exhaust gas of the oxyfuel kiln. And we thereby were able to study the variation of false air ingress between 4 and 8% of the flue gas volume, which is important to also assess the efficiency of the whole system. Now I start with the modeling. So from the complete system, which you see on the right lower corner, you see all components of this model. We have here the preheater, the calciner, the rotary kiln where the clinker burning is performed, and then the cooler. And the gas recirculation is really a circle which is going from the preheater through filters and an organic Rankine cycle for energy recovery, a condenser, and then a part of the gas is fed again to the cooler, and the other part of the gas is transferred to the CO2 purification unit for further transport and storage. In this Oxyfuel process modeling, the main interest was really whether we were able to replicate the heat transfer profile along the kiln, and this you see in the top right side in this diagram, where the original reference model was a BAT 3000 in the blue line, and the first result was a red line in the modeling of the Oxyfuel process, which was not 100% suitable for really burning quality clinker. We had therefore to adjust the process, and this Oxyfuel refined model result shows that the heat transfer profile was really replicating the original, which then also tells us that with this adjusted heat profile, we can again produce high quality clinker. And of course, as I said, the false air ingress was modeled and variations of it were investigated. And of course, it was also clear that as soon as you have false air ingress, the energy demand in the CO2 purification unit increases. And this means that for minimizing the false air ingress, you need careful maintenance in such an Oxyfuel system to minimize really any air in leakage into this gas recirculation system. We come now to the testing and experiments that were done here first on the Oxyfuel clinker burning technology. In this, we learned that modern cement kiln burners can really be used in the Oxyfuel operation. And so they are versatile enough to adjust the process in a way that we are replicating the right heat transfer profile. And these burners are already ready for Oxyfuel technology, let's say. The similar radiation profile was achieved, and it was also shown in these experiments that the amount of oxygen enrichment in the burner is indeed a new parameter which adjusts the heat transfer profile and the temperatures in the kiln. So this is a parameter which allows to really have the right clinker quality and to adjust the burning process in a way that is suitable for this Oxyfuel technology. When it comes to the calciner technology for the Oxyfuel process, this was in work package 8 of CEMCAP, we showed in the tests that the temperature increase, which was around 60 Kelvin, was replicated. This was best achieved by tests in which we had not only heating of the pipe from the outside, but also addition of fuel, like it is in the cement, in the calciners in real cement plants. And the challenge here is with this heat increase to minimize the heat increase in that way that the temperatures stay in acceptable boundaries for the equipment that is used in calciners. The heat transfer characteristics to the raw meal particles are the essential part also to avoid additional temperature rise and to minimize the temperature rise. Also, we learned that by decreasing the amount of calcination, which you see on the vertical axis in this diagram, you can, of course, further reduce the temperature to an acceptable level, which then means that the rest of the calcination, which is needed, has to be performed in the first meters of the cement kiln. Now we come to the Oxyfuel clinker cooler, and the prototype, which was built by IKN, has been successfully operated in the cement plant in Hanover. The clinker cooling was successfully demonstrated there in this industrial environment. One of the challenges was really to seal the cooler outlet against the false air ingress. And this is certainly a point which will demand special attention also in industrial scale projects, as we have there the extraction of the product clinker, and we need to prevent as much as possible the ingress of false air. The moisture and dust content in the recirculated gases needs to be minimized in order to assure trouble-free operation of the cooler, and therefore the layout of the condenser in such an oxyfuel system will play a key role in setting really minimum moisture content. One very nice thing of these experiments in the cement plant in Hanover was that we were able to also record some parts of this experiment in a short film. You can find this film on YouTube, and it really tells you in a short story how the testing of the world's first Oxyfuel clinker cooler prototype was performed and which challenges had to be really mastered to achieve these results in the CEMCAP project. Also, the very first clinker cooled with Oxyfuel technology was sampled from these experiments. And you see that we have prepared these samples in very nice small cylinders here. And not only this, but also the clinker sample was put to the laboratories in VDZ, and we were thereby able to demonstrate that in this situation with cooling in CO2-rich gas, we were able to achieve high-quality clinker product. The cooling gas, which was rich in water in some moments during the experiment, showed that there was a very limited amount of alloy decay, but that this had no negative impact on the strength development in the final product. So we are certain that the quality can be maintained, and also that in a real oxyfuel system, this water content can be minimized by an efficient condenser working in the recirculation cycle. We can then conclude that really the next step for this Oxyfuel technology is a demonstration of a complete oxyfuel capture system in a cement plant, and this would be at TRL7 or TRL8 level in industrial scale. The plans of the European Cement Research Academy, ECRA, for having such an oxyfuel capture demo project you can find in a press release on the website indicated here. We are now one step closer to the implementation of the Oxyfuel technology in the European cement industry, and this we have summarized in a blog, which you can find on the first link. We have also summarized these results in a very nice workshop in Brussels last week, which was called Carbon Capture Technologies in the Cement Industry, and you find all the posters also from the work packages on Oxyfuel on the corresponding website of the CEMCAP project. Finally, I want to acknowledge all the contributions of many people to these experiments and also their dedication to the project, which were the basis for really mastering all the challenges on the way of these experiments. Of course, also the funding that was provided from European Commission Horizon 2020 project, and you will find the final documents on the website of CEMCAP. Thank you, and I'm open for questions to the Oxyfuel technology, together with Christine for questions on the other technologies and the CEMCAP project as a whole.
Yes, hello. So now it's open for questions. You can raise your hand in the GoToWebinar. One question was sent and I forwarded it to you, Kristin. Kristin? Kanske inte någon.
Sorry, I was on mute. I had muted my
Okay.
mic myself. Yes, okay. Yeah, will there be a CEMCAP 2? What should we say? Maybe. It seems like there would be need for further work. Yes, definitely. But there are also other projects like the ECRA CCS, the Clinker project. So we'll see.
Okay, it seems that there are no further questions of the 12 attendees. So should we make Mari as a presenter now, as there are no questions?
Yes, do so.
Okay. Okay, Mari, now you're a
Yes,
presenter.
so my name is Mari Volsund and I work in SINTEF Energy Research. And I'm going to give a presentation about retrofitability of CO2 capture technologies to cement plants. And this work is done as a part of the CEMCAP project. And the motivation of the work is that 79% of the global anthropogenic CO2 emissions comes from the cement industry. And CO2 generation is an unavoidable part of cement production, and therefore CCS is the only viable option to significantly reduce these emissions. And one aspect that is important for cement plants is that they in general have a long lifetime. They can be they can operate for 30 to 50 years, and in many cases much longer than that. And therefore it's important for CO2 capture technologies that they can easily be retrofitted to existing plants. So that's the main motivation for this assessment of retrofitability of capture technologies. The technologies that we have evaluated are the MEA technology, which is used as reference in CEMCAP, and the CEMCAP technologies, the Oxyfuel process, chilled ammonia process, membrane-assisted CO2 liquefaction, and two types of calcium looping, the tail end configuration and the integrated entrained flow configuration. And as you can see on the figure here, most of these technologies are post-combustion technologies, but the Oxyfuel technology and the calcium looping integrated technology are more integrated with the cement kiln. So the approach that we have used in this work is that we have found different aspects that a plant owner would consider if it wants to retrofit his plant. And for each of these aspects, we have done a qualitative assessment. And the first aspect is a very important one. It's the impact that the technology would have on the cement production process. It's very important that the quality of the product is maintained, and also that the operability of the plant is not affected by the capture process. The next aspect is the need for additional equipment, and in particular the space or the footprint required by this equipment, because in some plants the space can be quite limited. The next aspect is the need for additional utilities and services. For instance, if you need a lot of power for the capture process, you could have problems with the capacity of the local grid. And also, if you need a lot of additional coal or natural gas, you need to be able to handle that. Then we have evaluated the need for or the introduction of new chemicals or subsystems at the plant, because this could require that you introduce new procedures and routines at the plant to make sure that you have a safe operation. And also you could possibly need permits from the local authorities. And the last aspect is the experience or the amount of experience that is available with the process. So as I said, we did a qualitative evaluation of these aspects, and we have used a color coding system. So if we say that a technology is green, then it means that the retrofitability with respect to that aspect is quite straightforward, and you don't need to pay a lot of attention to that aspect. And if we say that it is yellow, then it means that some attention is needed. But in most cases, also here, it would be straightforward to retrofit that technology. And then orange means that either you need to pay special attention to this aspect, or that further assessment is needed. And red means that we have found that retrofit is actually not possible. So now I will go through each aspect one by one, and I will start with the impact on the cement production process. So what is clear for the post-combustion technologies is that in general they don't have any impact on the cement production itself. You just send the flue gas to the technology, and you don't make any changes to the kiln system. And also, when you install the technology, you just need a very short production stop in order to reroute the flue gas. So therefore, we have assessed all the post-combustion technologies as green. For the oxyfuel process, you have a bit more impact on the, or quite some impact on the cement production system. You have introduced a new gas atmosphere, both in the clinker cooler, the rotary kiln, and the calciner and the preheater. And you're also dependent on the recycling of CO2-rich gas to the system and the control of this. So for this technology, you have a bit higher risk, and therefore we have evaluated this as orange. For the calcium looping integrated technology, you also have quite some impact on the kiln system, but it is limited to the calciner and the preheater. So you don't have as high risk as for the oxyfuel process, but you still have quite some impact. So it's evaluated as yellow. When it comes to the need for equipment and footprint, it is clear that some attention is needed for all technologies, because all technologies need some additional equipment, and this will need some space. However, for the post-combustion technologies, you can install this equipment more or less anywhere at the plant. You don't need to install it close to the kiln, and that is a benefit because often the space available close to the kiln can be limited. So the post-combustion technologies are evaluated as yellow. For the oxyfuel and calcium looping integrated technologies, however, then you need to install some of the equipment really close to the kiln, and these technologies are evaluated as orange. For the need for utilities and services, then you need some new utilities for all technologies. For amine and chilled ammonia process, you need quite a lot of steam and some power. For the Oxy Fuel Technology and membrane-assisted liquefaction, you need a large amount of power, especially for membrane-assisted liquefaction. For calcium looping, you need additional coal, but in the process you also need power, but also in the process you generate power from excess heat, and therefore, depending on the case, you might need to import some power, or you would need to export power. And if you want to export power, you also need the infrastructure for this. So as you see, all technologies need some utilities and services, but in most cases, this could be handled quite easily. So all technologies are evaluated as yellow. So when it comes to the introduction of new chemicals and subsystems, then for MEA, of course, you need to introduce large amounts of amine at the plant. For oxyfuel, then you need an ASU and possibly an organic Rankine cycle. For chilled ammonia, you introduce large amounts of ammonia and also a refrigeration system. For membrane-assisted liquefaction, you just introduce a refrigeration system, and for calcium looping, you introduce an ASU and a steam cycle. And out of these chemicals, it's expected that the introduction of amine and oxygen and ammonia is most challenging, while the introduction of a refrigeration system should be quite straightforward. So therefore, the membrane-assisted liquefaction technology is assessed as green, while the others are assessed as yellow. So the available experiences for MEA, or in general amine, we have operation for a coal power plant at the boundary dam of the complete system in full scale. But it has also been tested in a large pilot at the Norcem Brevik plant for cement. It has captured 370 tons CO2, and it has been tested for 2,700 hours. For the Oxyfuel technology, the full system has not been demonstrated, but as you saw in CEMCAP, we have tested the different tested pilots of the different units. For chilled ammonia, the process has been tested in a large pilot for coal, a 50 megawatt thermal power plant at the Mountaineer plant. And it has been shown in pilot testing in CEMCAP that it is applicable also for the cement process. So these technologies are evaluated. Amine is evaluated as green, oxyfuel as orange, and chilled ammonia as yellow. For the membrane-assisted liquefaction technology, the full system has not been tested together yet, but we have tested membranes in CEMCAP, and also at Norcem, membranes have been tested in cement conditions. And the liquefaction process has been tested within CEMCAP in a pilot. The calcium looping tail end technology has been tested at the La Pereda plant, a 1.7 megawatt pilot, and it has been shown that it's applicable also to cement in the pilot testing that has been performed in CEMCAP. The calcium looping integrated technology has been tested in lab scale in CEMCAP, and it will later be tested in large scale in the Clinker project. But if we look at the testing that is done now, we have assessed membrane-assisted liquefaction and calcium looping as orange, and also the calcium looping integrated as orange, and the calcium looping tail end process is assessed as yellow. So to summarize about the retrofitability of the technologies, we can see in the matrix here that most aspects requires at least some attention when it comes to retrofitability. But we have not ended up with a red square for any technologies, so there are no aspects that have led to that any of the technologies are assessed as not suitable for retrofit. But you can also see that there's a difference here between the post-combustion technologies and the more integrated technologies. In general, the post-combustion technologies are more easy to retrofit in the cement plants. Yeah. So in this slide, you can see the CEMCAP partners, and we would like to give acknowledgements to the European Union's Horizon 2020 program, and also to the Swiss State Secretariat for Education, Research and Innovation.
Okay, Marie, are you finished?
Yes, I'm finished.
Yes, thank you. So now the attendees can ask questions, and I'm gonna unmute Juho Lipponen because he asked a question. Juho?
Yes, I am here. Can you hear me?
Yes.
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 Well, wonderful. Hopefully you cannot see me.
No.
I actually heard the presentation at the GHGT conference last week, and I found this really interesting. And I was wondering if you have done any analysis on like what the scale and potential of the retrofits would be, either in Europe or globally, or are there any, or would some country have done this type of investigation? And I know it's probably very hard, and you might need lots of plant level data, but what have you got a sense of scale of retrofitability globally? That's my question. Thank you.
You mean how many plants?
Yes, how many plants and how many millions of tons of CO2 we could potentially say capture by retrofits?
No, that has not been a part of the project, but it's of course it would have been very interesting to get numbers for that. Yeah, but it wasn't done here.
I think
Okay.
CEMCAP was more technology. I don't know if you have a comment there, Johannes. Maybe you know more about what's been done worldwide about estimations.
Yeah, well, when it comes to the global perspective for carbon capture technologies in the cement industry, I think the new IEA technology roadmap, which was formulated together with the Cement Sustainability Initiative and was published in April 2018. This is giving a little bit the perspective, but most likely I would also say this is a perspective of what is needed to achieve certain CO2 emission reduction targets in this scenario of the International Energy Agency. The conclusion from Marie's presentation, I would say, is that at the moment we have no showstop for any of these technologies. And having available this handful of technologies which seem all suitable for carbon capture retrofit, we have good options that for every cement plant you can find a technical solution for the capture. But the challenge will then, of course, also be to not only capture the CO2, but also to transport it and to either store it permanently or to use parts of the CO2 as a resource for carbon-made products. So I think the challenge here to really assess how applicable is this is to say, yes, we have very good availability of key technologies for capturing and for retrofitting existing plants. And then the local conditions also for the transport and storage of CO2 are also important elements in assessing that.
Thank you.
Thanks, Johannes.
Okay, so it seems that there are no more questions. No hands are raised. So, Christine?
We say raise your hand now or be forever silent. This webinar will also be stored on, it will be available from the CEMCAP website, so people will be able to look at the presentations again afterwards.
Okay.
No further questions?
Still no hands.
I think that we can end it.
Okay, thank you. And then
Thank you very much.
Yeah, we'll meet again at 2 o'clock for some of us.
Yes. Thank you very much to all the presenters, to Mari and Johannes, for joining in on this webinar. It was planned quite recently, and thanks to all the attendees. And I hope you will join us again at 1 o'clock.
Okay, bye-bye.